Ladies and gentlemen, hello and welcome, coming to you not quite live from One Take Studios, where I'm going to try really hard not to mess this up today. Alright, we are talking about the normal approximation to the binomial distribution. I'm going to show this to you because it's a thing. However, I'm really not sure why this is still a thing in our current age of technology, so if you find out why we still need this, can somebody please let me know? I'd appreciate that. Again, I'm not approaching this from an AP perspective. I'm approaching this from, hey, we have technology, let's use it, and let's learn how to use it and what the numbers mean sort of perspective. All right? So, normal approximation to the binomial distribution. Dun, 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 dun. Okay, this is me faking excitement with my exclamation point here. As n increases, the binomial approximation approaches normal. Yay! Okay, what does this mean? If we get a large enough sample size or number of trials for a binomial circumstance, all of a sudden it starts behaving like we have a standard normal curve. Shoot, should I put the word standard there? Probably not. It starts behaving like a normal curve, which means that under certain circumstances, we can abandon everything that we've learned about binomial and just pretend it's normal instead. However, there's quite a few changes we need to make that actually happen. So, for starters, how do I know if my n is going to be large enough? Because maybe it's not. What's the parameters for this thing? All right, so things to think about. Under typical circumstances, so not talking binomial at all at the moment, just talking regular stuff, regular distributions, we say that our data behaves normally. A really tall stick on the end there, behaves normally if the x distribution is normal, because somebody's established the fact that it's normal, it fits normal parameters, or my sample size is greater than or equal to 30. Alright, so this is under normal circumstances, not binomial. This is just normal stuff. We say that, hey, it's going to behave normally if I know that the distribution is normal, or if I have a sample size of 30 or more. This is different, because we are starting from the perspective of binomial. And so the n is greater than or equal to 30 will not work here. Repeat, this will not work for binomial circumstances. Instead what we are doing is we are saying, alright, if n times p, refresher here, n is the number of trials in our binomial problem, and p is the probability of success. If I multiply n times p and I get a value that is greater than 5, that's a good sign. But if I also multiply the number of trials times the probability of failure, and that is also greater than 5, then it will behave normally. So, if this is true, then we can use normal. This is under typical circumstances, not binomial. It has to be 30 or more, or we have to know that the distribution is normal. But if we have binomial, and we would like to use normal instead, we are looking, do both NP and NQ have values greater than 5? Because if they do, then it behaves normally, and we can abandon our binomial stuff and work on our normal stuff instead. Alright, so that's thing 1. Thing 2. Thing 2. There's also this fun thing called a continuity correction. Alright, so get this, continuity correction. What does this mean? Well, let's see here. Oh, what does that mean? Okay, so discrete random variable is what we have for binomial. Binomial is the whole thing with we got success or failure, and we could have 1 success, or 2 successes, or 3 successes. This is discrete. Okay. Can we have 2.7 successes? No. So, in binomial circumstances, we are discrete random variables, but again, we're trying to change this to something normal, and normal is continuous. All right? Think about this. All right? Think bar graph versus histogram. What's the difference between these two? Bar graph is kind of the representation, sort of, do I mean that? Yeah, sort of, for, excuse me, binomial stuff, and histogram is sort of what we're heading towards for normal stuff. The difference between these two? is the gap between the bars. So the difference between discrete and continuous is the gap between the variables. All right, continuous actually has the 0.5s and 0.2s and 0.7s, and discrete is just supposed to be 0, 1, 2, 3, 4. So how do we compensate for the difference between the types of variables that we have here? And that's going to look something like this. All right, our boundaries will need to be adjusted. This is our continuity correction. Our boundaries will need to be adjusted because we can't just say I'd like between 4 and 7 successes. We're going to do that with a plus or minus a half, plus or minus 0.5, just like we would do with our histogram bars. So if normally I'm looking for the probability of, what did I say, 4 to 7? I think I said 4 to 7. You would use boundaries not of 4 and 7, but you would use 3.5, dropping by a half, and 7.5, going up by a half. So we have to make this correction to our boundaries, to our lower bound and our upper bound, going a half point down and a half point up, to compensate for the fact that we are changing the type of variable that we have. Okay, so we have to have NP and NQ greater than 5. We have to change the boundaries to make that happen. What else do we need? Well, what else do we need? Let's see here. Let's ponder that, shall we? Here's a problem that I made up, although I actually did Google this. So in 2016, 70.3% of eligible citizens were registered to vote in the U.S. So let's say that we have a group of 500 eligible citizens sitting in front of us. What is the probability that 400 or more are registered to vote? We're looking for a probability. Okay, and actually I'm going to slide this out of the way to give us some space. And how do I know that this is a binomial problem? Well, okay, so think success or failure. They are either registered or they are not. So this is absolutely going to be binomial, and we're going to see if we can adjust it to fit under these circumstances and run it as though it was a normal problem instead of a binomial problem. All right, what's that going to take? Okay, let's see. Probability of success, 70.3. Sample size, 500. Okay. We can't even move forward unless we know that NP and NQ are both greater than 5. So let's think about that for a second. NP and NQ have to both be greater than 5. So we're talking 500 times 0.703. 500 times 0.703 is, yeah, I'm going to jot that down there. This is not having the best of days. 351.5. So n times p is 351.5. Is that value greater than 5? Yes. Yes, it is. Check mark. Accomplished. So far, we're so good. We can keep moving forward. This, by the way, is Q, which is the probability of success. This is just going to be the flip side of the 500. So this is 351 out of the 500. This is the remaining section. Is that going to be greater than 5? Goodness gracious, yes. Absolutely yes. All right. So we are absolutely meeting these circumstances. This is 351. This is well over 100. We're set to go. We can continue. Okay. So think about what we need to run normal CDF in the computer. Think about the things that they're going to ask for. They're going to ask us for a lower bound, an upper bound. They're going to ask us for mu and sigma. So do we have enough information here that we're going to be able to do this? Even though it's binomial, could we run this? All right. Well, we're looking for the probability that 400 or more are registered to vote. So think about lower upper. 400 or more, and there are 500 people. So normally we would say 400 to 500. But we need to push out our boundaries by half to compensate for the variable change. So when I go to put this together, I actually want to use a lower bound of not 400, but 399.5. And when I go to use the top end of 500, I'm actually going to bump that up by half and call it 500.5. So we are taking our high and our lower, bumping them both out by a half point to compensate for this change. All right, so that's our continuity correction. Do we have mu? I don't know. Do we have mu? I got P, I got N, I got Q. I can probably figure out Q. How do I find mu and sigma? Oh, that's right. There were formulas for that. Remember, if we talk about mu, was n times p. Oh, we just ran n times p, which means in this case, for this problem, we are talking, I'm going to write it out actually though, 500 times 0.703, and that had a value of 351.5. That's going to be our mean, all right? That's mu. So we're going to need that for this. So 351.5, there we go. And do you remember the other formula? Sigma was the square root of NPQ. So that's the square root of, again, 500 trials times P, which is 0.703, times, I don't trust my brain at the moment, it's doing weird things. And then my calculator is turned off. Thanks, appreciate that. Alright, I'm going to go with 1 minus 0.703, make sure I'm right. Oh yes, okay, good. So Q is the complement of that is 0.297. So if we crank that through, we should get what here? Square root of 500 times 0.703 times 0.297. Survey says this has a value of 10. I'm going to call it 22. It's 0.217. So that's going to be our sigma. So when we go to put this in the calculator, in order to be able to pretend that this is not binomial and pretend that it's normal, we have to check to make sure that it behaves normally, which it does. This passes our circumstances here. You know what? Just for the fun of it, 0.297 times 500, just in case you don't believe me, this is going to be 148.5. All right. So these are both greater than 5, so we can proceed. Our lower and upper, 400 or more, that's 400 to 500, but we did our boundary correction of 0.5 each direction, 0.5, 0.5. Okay. We had to calculate mu, which we did, and we had to calculate sigma, which we did. Now after all that stuff, we can go to our calculator and say, please, calculator, can you pretend that we don't have something binomial? We would like to show you something else. So we come over here and say, all right, I'm running this as normal. I am looking for a probability. So probability, we've got that. It is a distribution, so we're going there. It is normal, and we're looking for a range of things, so normal CDF makes sense. Lower bound, putting in the numbers that we agreed upon, so we're calling this 399.5 for the lower, and then upper bound is going to be 500, 500.5 for the upper. We are saying that we know that mu is 351.5, 351.5. Is that a point? Yes, there we go. Why? Because that, there we go. Okay, 351.5, and we know that this is going to be 10, I mastered the 0 that time, 0.22, 0.22. All right, now, what do you think? This is a probability, high or low? Where do you want to go, high or low? Survey says, whoa, dude, that's kind of tiny. How many zeros is that? 1, 2, 3, 4, 5, I think. 1, 2, 3, 4, 5, yeah, there we go. That is the probability that out of a group of 500 people that are eligible to be registered to vote, that 400 or more of them are actually registered to vote. I can do this, so can you. All right, so if I jump back to my other screen for a second here, let's think about why that's so small. This is my mean, this is my expected value. My expected value is 351. 400 is significantly above that. How significantly above that? Well, think about this. If our standard deviation is 10.2, all right, most of our data we expect to be within 2.5 standard deviations of the mean. That means that we expect that most of our data should be within 25 each direction of 350. This is definitely well over that, so it is not super likely, and that answer actually makes sense. All right, so again, a lot of things happening here. This is under normal circumstances. This is if we want to use the normal stuff on binomial. We have to make this correction. We have to do all the calculations. Why would we do this? Again, I'm not entirely sure. I'm showing it to you because it's a thing. It exists, but quite frankly, I can do half of this much work, less than half of this much work, and run it through binomial PDF or CDF in the calculator and be done. So, it's a thing. Humor me. Have fun, all right?